61A, Lecture 25 Q&A. There were no questions about the lecture, but there were some questions about lab, homework, and past exam problems.
One of my favorite things, John, about that video was the use of the VHS tape to play the videos during the talks.
Wasn't that great?
Yeah. Yeah, that brings me back. So back in the day, by the way, when we used to do presentations, this is before we all had laptops, we would take pictures of our physical slides, develop them as 35 millimeter slides, load them into a carousel tray, get on an airplane with that tray, show up at the conference, hand some guy that tray, and they would literally put that tray on a carousel and like flip through it. And without fail, every single talk had like at least one slide upside down, and the audience was all sort of doing this, trying to see the slides.
That sounds excellent.
The good thing about that, by the way, was, now when you go to conferences and talks, everybody's on their laptop and device. So back then, there was nothing to do. You just listen to the goddamn talk. Mm-hmm. Now it's hard to get people's attention.
Yeah, now at conferences, everyone's writing their talk that's going to happen in 3 hours. So.
I like sitting in the back because I could see everybody else's talk being worked on. I'm like, all right, what are we doing here if we're all working on our talks?
Exactly.
I miss those days.
Yeah, I took one class from a postdoc who decided that transparencies were better. And I think he was right. Like he had this huge stack of printed out transparencies, and he put each one on the overhead projector, and then he'd write on it as he was lecturing, and it was very nice. But I did get a panicked email to the whole department once saying my 4-foot high stack of transparencies has gone missing. It's like my life's work. Has anybody seen it? So
I had the problem where I used to go to talks, and every once in a while they were in a box, and I would drop the box, and the slides were like all over the place. See, that's a real. My favorite thing that I ever did. This is what I did when I interviewed for my job at Dartmouth. So we had this problem with transparency. It's called keystoning. So if the projector was very close to the screen, the slides would be really distorted because you were projecting sort of upwards.
Yeah, so the bottom
and
would
so
be there. Yeah.
I had 3 versions of my slides that I printed with the inverse distortion.
Oh,
and so when I put the slides down, they were almost parallel. And people were just complete. This, by the way, this is what passed for high tech 20 years ago.
That will definitely get you a job. That's amazing.
Yeah. And it was just and I had a slide showing it's just a homography. Oh, by the way, it's if you were present for the first lecture where I talked about the license plates, it's the same map that did the license plates.
Very nice.
Yeah. All right.
Okay, so we're in lab 9, question 4, number of binary trees, where you take an n and it tells you how many different binary trees have exactly n leaves. And it points out that there is a closed form solution.
I think that's
unbalanced parenthesis, which is unacceptable, but there it is. So this closed form solution, let's see what that looks like. It's just pointing to the Wikipedia page that says like there happens to be a formula for this thing.
All right. Well, Michon's right. That's not really acceptable.
But the goal here is actually not to just write down that equation in code, but instead to think about this recursively. So just to get you started, if you want to build a full binary tree with 3 leaves, well, you got to have some number of leaves in the left branch and some number of leaves in the right branch. In this case, there's 2 in the left branch and 1 in the right branch. Once you've decided how many are left and how many are right, you can just use recursion to count up all the ways of completing the left branch. The ways of completing the left branch is all the full binary trees with 2 leaves, because we decided there are 2 over there. And on the right branch, that's the number of full binary trees with 1 leaf, because there's a 1 there. And so both of those can be counted with a recursive call.
So the basic idea is you decide, okay, I'm looking for 3 leaves. Okay, so it could either be 0 on the right, 3 on the left, 1 on the right, 2 on the left, so on and so forth. And then once you've established that for the top level, well, then everything else is just recursive.
And then there's
I don't know how to do this non-recursively, by the way. It's not obvious to me.
Yeah, I mean, there's this formula, but you know,
Yeah, well, besides that.
that's all. I mean, this it looks like a recursion problem. Now, I mean, I guess what's interesting here is that it's an unusual way of combining the two recursive calls. So, you know, we can talk about this for just a minute longer. You know, okay, so if n is 1, then there's just one tree. We saw that as a demonstration, right? But otherwise, let's forget the template for a little while. We'd want to go through all the ways of dividing up. And so we got to have at least one on the left. And then what's the most we could have on the left? Well, we could have up to n minus 1. So we'd go to range n. How many left is this?
I think you need an I in there, John, or something.
And then how many on the right? Well, the rest of them. And then we can figure out the number of trees, possible trees on left. That's just a recursive call. For the number of leaves that are on the
variable names are getting a little long.
Okay, well, we'll trim it a little bit. That was absurd. And how about on the right? Well, that's symmetric. But then you do have to think about what you're going to return, which is that if you have 8 different ways of building left branches and 5 different ways of building right branches, how many different ways are there of building a whole tree? Well, you can take any from the left and any from the right. So for any of the 8 on the left, you have 5 different options on the right. So for the first one, you have 5. For the second one, you have 5. For the third one, you have 5. Fourth, 5. So what's 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5? That's 8 times 5. There's like a notion of a total, which you get by multiplying together the left and the right. But that's just for one split. Now you have to think about all the different splits that you have. So really, we should have a total that starts at 0. And this is just describing if we picked a particular number of leaves on the left, how many total trees would there be? And we need to add that to the total and return the total. Okay, so now you can think about how to get that all in one line, which you can do with some, you know, we're making a sum of a bunch of different options. So maybe there's a list comprehension in there somewhere. But I just tried to describe why there's a product, like a multiplication in the middle of this. It's really because you're saying, like, I can take any one of the options from the left and any one of the options from the right and pair them together. And that's how you get a full binary tree.
There's a good lesson here, too, is when you see these templates, I always feel like, you know, I've got like one hand tied behind my back. But when you're thinking about the problem, you can break free of the template, figure out how to think about the algorithm, and then go back and shove it into the template. That's how I usually think about these problems. You know, when we talk about clever, although I was teasing John a minute ago about his variable name, there's a reason to do that. It's not just good programming style. It's particularly with recursion. It sort of helps you jump over the cliff. Yeah. Because you can see what this thing, if you believe that this is what it is, well, then that's what it is.
A follow-up question was why we're multiplying.
Let's say that I give you, let's see if this analogy works here. I give you 2 things in my left hand and 3 things in my right hand. Yeah. And I ask you, what are all the ways of combining them? Yeah. Well, okay, so I can take 1 thing from the left hand and put 3 things from the right. Wait, no, that's not quite what I want. Is that right, John?
Yeah, I think like if you have A, B, C in one hand and you have 1, 2 in the other hand.
Yeah.
Like, what are all the different combinations you could have? You could have A1, A2. You could have B1,
Yeah.
B2. You could have C1, C2. That's 6 things. That's because it's 3 times 2. So like if you ever think about how to pair something from your right and something from your left, what are all the possible ways of doing that? You end up multiplying.
Yeah, so we're looking for we're not summing them up. So it wasn't like oh, here's the answer for the left, here's the answer for the right, and it's the sum of them. We still have to combine everything. And we can combine them by picking all the different ones from the left hand, all the different ones from the right hand, and doing all permutations of those. Yeah.
Okay, let's take a look at homework 5, question 6, which is one of the optional ones called yield paths. Define a generator function path yielder, which takes a tree of value and returns a generator, which yields each path from the root of t to a node that has that label called value. T is implemented with the tree class. And each path should be represented as a list of the labels along the path in the tree. You may yield the paths in any order. Oh, and they gave us some starter code. Let's see what they did. So, I guess we're gonna have to make this one big. We have an example tree here. So 1 is at the root, 2 and 5 are its children, 3 and 4 are children of 2. Oh, sorry, 3, 4, and 5 are children of 2, and 6 is a child of 4. And then when we call path yielder on 6, it finds this one path to 6, which is that you have to go from 1 to 2 to 4 to 6. Okay, then there's the list. But since there are 2 different 5s, then we need 2 different paths, the 1 to 2 to 5 path, and also the 1 to 5 path. And it says like iterate a little bit. So sometimes you find that the label of the tree, the root label of the tree that you're on, is equal to the value you're looking for. If so, I think it's time to yield a list containing just that label, or just that value equivalently. So that would handle the case if we were doing path yielder of 1, and we wanted that list containing just 1, like a really short path that's only got 1 element in it. The other thing is that this will allow us to build up longer lists because we've returned a list that's got the right last value in it, and then we're going to have to add stuff onto it to get the full path that we want. Okay. So we're going to go through every branch. For each branch, it might contain a bunch of paths to this label we're looking for, and we need access to every one of those paths in the branch so that we can then yield paths in the whole tree. Here's an opportunity to use recursion. If I call path yielder on the branch and the value I'm looking for, what I get back is a path through the branch. But what I really want to yield is a path through the tree. And so I just write that down. I want to yield a path through the tree, which is everything through the branch, but it also has the label at the front. Might be something like that. Nope.
Uh-oh.
Probably need to know what
T2 is not defined, it's saying, yeah.
Know what a tree is. Okay, so
There we
now it
go.
works.
Next, we did the spring 2020 midterm 2, question number 1.
So this question involves plucking the leaves off a tree one by one. A tree with unique positive integers, no repeated labels. Plucking order for a tree is a sequence of unique positive integers that are all labels of t. And a valid plucking order if the plucking order has all the labels in t and there's something special about the order. The labels for each node of t appears after the labels of its descendant nodes. So you have to pluck the leaves, and then you can pluck the parents of the leaves, and then you can pluck the parents of the leaves, etc. Okay. I think we probably have to do A in order to do B, so let's just do the whole thing. Implement order, which takes a number tree called redwood. It returns a valid plucking order as a list of numbers. If there is more than one valid plucking order, your order function should return any one of them. Oh, how nice. We have something that's empty. It's called redwood for some reason instead of t, but redwood.branches. it seems like we can just get a plucking order for the branch and add that to our plucking order. You have to know which method to apply. If you have a list already and you're trying to add a bunch of elements from some other list, then the way to do that is with the extend method. Okay. All right, here's the question you actually asked about. B, implement pluck, which takes a number tree called pine, okay, and returns a function that is called repeatedly on the elements of a plucking order. If that plucking order is valid, the final call returns success. Otherwise, if one of the repeated calls is on a number that is not part of a valid plucking order, the error string says, hey, not valid. Interesting. So we take a tree. We then get a function back. We start calling it on numbers. If they are a plucking order, let's see what happens. I pluck the 9, then the 8, then the 7, then the 6. I can't pluck the 1 yet because it's got stuff still, but I can pluck the 5 and the 4 and the 3 and the 2, and then 1 is bare. I can pluck the 1 at the end, and then it would tell me success. But if I ever try to pluck something out of turn, then it says, hey, not valid. Okay, cool. What a beast. This is probably the longest problem we've ever seen on a midterm. Let's read it together. Here's the function that we're going to return, and we return it right away. So the only reason that we're returning this function is because it has as its context the tree itself, so we can refer to the tree. That's good. We have this notion of pluck one leaf, which takes in something. Return a copy of cypress. Oh, it takes in a tree without a leaf K. And check that K is a leaf label, not an interior node label. Okay, so this is the moment where we build a new tree that's kind of like the old tree, except for we've plucked off one of the leaves. And then, okay, so however this does it, we'll figure that out later. We say non-local pine, which is interesting. I think non-local pine is going to mean we're going to change the tree we're talking about to one that has its leaf plucked off. If pine is a leaf, then it makes sure that it's the right label and then tells us success. Otherwise, we need to change pine to be the result of plucking a leaf off of the current tree. If is instance pine stir, oh, this says if plucking a leaf caused a problem, that problem is a string that says something like, wow, you screwed up. Oh, hey, not valid. And so we'll return that. Otherwise, we return the same plucker function that we had before, because we're just going to call it again. All right. So it seems like pluck one leaf has to not only build a new leaf that has one less build a new tree that has one less leaf in it, but it also has to sometimes return a string that says we screwed up. All right. So let's figure this out in a second. But this says if plucked branches equals, okay, so we're going to go through all the branches and build new branches. There's some condition under which we skip a leaf. And if we don't skip this leaf, then we pluck a leaf from the branch. And this might be a string, and if it's a string, then we're done. Otherwise, we probably put this into our plucked branches. Append the plucked branch. So this is how you'd build a new tree, is you'd have a new list of branches, you'd go through all your old branches, and you'd put in the new branch, which is like a plucked version of the old branch. And then at the end, we'll build a tree. And that tree is just the old tree, cypress dot label with the plucked branches. I feel like we're getting close. What does it mean to skip the leaf? Well, it has to be a leaf. I think that's a method. We'll check it in a second. And it has to have the right label. What was it called? Oh, not value, K. Why K? K is the next value we're supposed to pluck. Sounds about right. So this goes through, checks all the branches, gets rid of the one that we're supposed to pluck, and if it's impossible to pluck it for some reason, then it tells us so. But we still don't have this case where we're supposed to return that something has gone terribly wrong. When would that happen? I think that would happen if you look at the root of Cypress and it turns out that that root is the K as opposed to a leaf being a K. So here I'm assuming Cypress is not a leaf itself. And if it's the case that Cypress dot label equals K, that's bad. Why am I assuming Cypress is not a leaf? Well, let's see where we call it. We call pluck one leaf here, where we've already checked that this is a leaf and handled that case. So we know the initial call to pluck one leaf is on something that's not a leaf. And then where do we make recursive calls? Well, if this thing's a leaf, then we're going to skip it. So we must be calling it on a not leaf here. Miraculous.
That's the understatement, John.
Well, it helps that I did once upon a time write this question. Apologies to all students who ever had to take it.
Oh man, you put this on an exam?
Well, it was an experimental exam. The experiment didn't go very well. So this is the first time that we gave people an interpreter, and I thought that might help them a lot. Turns out it didn't help them very much.
That's a good homework problem, though.
And yeah, I mean, you know, the key to this question is really understand what you're trying to do. It's not about like memorizing some pattern you've seen before, but instead just focusing on, you know, like what exactly is the process that I'm trying to describe with the code. But the reason this is, you know, it turned out not to go well, is that there's all this like error handling of strings, and that turns out to be hard to process. But at least I had now given you a description of why it is the way that it is. Yeah, good question. So how would you approach a question like this? And especially if you read some part and you're like, I don't know how this part works. Well, I mean, I hadn't looked at this problem in quite a while. So it did feel a little bit new to me, although not entirely new because I wrote it. But I wasn't sure what was going to happen in here when I was reading the skeleton. So I kind of just skipped it as I was going. And I had this idea in my mind that that we'd like have a tree and we'd like remove one of the leaves, and then we'd have another tree and we'd remove a leaf from that. Like, and I was wondering, how's that going to happen? And I have a function to do it, but this has to be called many times. And so I ended up skipping ahead to here to try to look for the mechanism that involves just like removing one leaf at a time and doing it over and over again. And this part I think wasn't so confusing to me, whereas this, you know, upon skimming it, it seemed like quite a beast because there was a bunch of blanks. And you know, now it looks reasonable, but it didn't at the beginning. But this idea that we would kind of keep track of the tree that we were plucking from and then pluck leaves from it, I guess that is one entirely separate question from how exactly you go through and get rid of a leaf. So I think in a really big question like this, looking for ways in which you could solve one part and solve another part modularly might make it more manageable. Okay, so let's take a look at this. This is fall 2018, question 7. Trictionary is a pair of tree instances, K and V, that have identical structure. Each node in K has a corresponding node in V. The labels in K are called keys. Each key may be the label for multiple nodes in K. And the values for that key are all the labels of all the corresponding nodes in V. Okay, so K can have two labels that are the same. And if you want to know all the corresponding things for 2, well, you'd have to look up the corresponding labels C and A in the V tree. And so that's why we see here key 2 has 2 values. Lookup function returns one of the values. Lookup function returns one of the values for a key. Specifically, a lookup function for a node in K is a function that takes V as an argument and returns the label for the corresponding node in V. Okay, so remember V is a tree here. So a lookup function takes the whole V tree and tells you which label to get, or like gets one of the labels and returns it. Implement the generator function lookups, which takes a tree instance K and some key. It yields all lookup functions for nodes in K that have key as their label. The new lookup function is part of the implementation. Okay, so I said that other thing was really big, but this is big too. Okay, so I think we should learn how this works. You call lookups on some K tree, which is this one that's given to us as an example, and some value like 2. It gives us back a generator over 2 functions. Each of those functions takes this entire tree in, but the function knows something about like what path it's going to follow. And so it gives you the corresponding value for some particular position in K. So calling F, the first F gave us C, and calling the second F gave us A. So this question is kind of a mixture of traversing trees and also dealing with generator functions and higher order functions. So it's synthesizing a lot of topics in this course. But I don't think you have to like discover how to do it so much. It's like lookups is going to go through and find paths to the number 2, but it's going to encode those as functions, and those functions are going to go find the same path through V and give you the corresponding label. Okay, so how will lookups actually work? If something yield a function that takes in the whole tree and does something with it. Otherwise, we go through all the branches and we make a new lookup for everything in here. Interesting. These lookup functions, like F, they take a tree and they have to somehow get you all the way to a label that you want. I think the simplest case is if what you look up is at the top. So if it's the case for that K, which is a tree's label, is equal to the key that I'm looking for, then that means the corresponding value label is right there at the root. So if I took in a tree full of values, I would want to return the one at the root. Otherwise, this key that I'm looking for could be in the branches somewhere. And so I'm going to go through all the branches, but this doesn't go through the branches. It goes through them by index for some reason. Well, we see the reason is that we use the index here. And we've got a hint here that we need like a lookup function already, and then we're going to build some new lookup function that basically uses this I somehow. So I'm going to put in a sketch of what I think might work, and then we'll take up new lookup and see what it does. I think if you want to introduce this name lookup, really we're going to have to go through all of the different times that key appears in this branch and get a lookup function for it. That sounds like a use of recursion. This is, I guess, quite similar to the problem we just did. Where here, we're not going to look it up in K, but we're going to look it up in a branch of K. Can't type. But we're still looking for the same key that we were looking for before. And this says yield a new lookup. So let's think about what this function would do. This function would look through a branch of V and find the corresponding values that match the key. But we want to look through all of K and find the corresponding value. So we build a new function, here it is, that takes in the whole tree V it has to look up within one of its branches I, the label that we're looking for. Where I'm assuming here that f is a lookup function for a branch of V. So what does new lookup do? Basically, like if you have a way of looking from here and finding, or sorry, let's do it over here. If we can look from here and find the A, what we're building is a function that can look from here and find the A. That's what this does. And then how are we building all of the functions that find both the C and the A? Well, we're going through all the different branches. So here's this branch, and this branch. And then we're going through all the times that I found the key in this branch, which is only here and here. I'm taking the function that knows how to look through here and find the corresponding C, and the function that looks through here and finds the corresponding A, and building new functions that can look from the top of V. Oh, that was a mess. Questions? Yeah, great question. So the question is, when would you do this and how does it relate to everything else that you know? This is quite abstract, but the following pattern shows up a lot, which is that if you want to build something that is, 4 things long, you start with something that's 3 things long, and you put something on the beginning, or sometimes the end. Linked lists look like this. You've seen this pattern when just using regular lists. Here we're seeing it using functions, where a function could be representing most of a path, and then we're building a new function that represents an even longer path, basically just by like sticking something on the front. Now, the way this function is implemented is by calling the function that represents the rest of the path. And so if you call G, you're kind of calling the whole path. Now, why would you want to call a whole path? Well, calling a path is like doing something with a tree. In this case, we're extracting a particular label from the tree. So in that sense, it does look like the same concept you've seen before, but certainly in a different way. This is now using kind of the mechanics of functions to do what you could otherwise do with a linked list. And Yeah, and knowing that you could achieve the same thing in different ways is part of computer science, but this is like really a new thing that was presented to you on the exam as like a new way of synthesizing existing ideas that you know how to use functions, you know how to use linked lists, you know how to use paths, but here you're asked to kind of put them together in kind of a new method. Okay, so let's finish up by explaining why yield new lookup I lookup again. Okay, so let's focus on an example. The example will be when we're looking for the number 3. We have not found it at the top. It never showed up here. We did get one lookup in this branch. And so if I call lookups on this branch, then I get a lookup function. But I called lookups not on the whole tree, but just on the branch. And that means that the lookup function I got is really only prepared to process this branch of the corresponding V tree. It knows how to take in this branch and find the S. But it doesn't know how to take in this whole tree and find the S. So we need to create a new function that is based on the one that knows how to find the S in this branch and can instead find the S in this whole tree. That's why we call new lookup, where I is the index of this tree, index 1. And lookup is the function that can take this branch and find the S. And then what we do is we get that branch and find the S.